Alright, so we're going to look at limits in a slightly different way. First, we're going to look at them the normal way, see if we can figure out the height of a function as x is approaching some value. But then we're going to use it for some applications. So just to go over some actual pretty typical limit problems, first we want to consider the function, the polynomial, x squared plus 2x minus 5. And so we want to figure out what's happening around x equals 2. Not x equals 2 exactly, but around x equals 2. So pretty much that means for us from the left and from the right. Get closer to 2 from the left and from the right. So if we were to pick some values as x gets closer to 2 from, let's say, the left, 1.5, 1.8, 1.9, it looks like our values are getting closer to 3. And we could keep that going if we wanted to. Now we want to do the same thing from the right. So from the right, we're going to pick 2.5, 2.2, 2.1 and get closer to 2. And again, our values are approaching 3, getting closer to 3. So as x approaches 2 from the left and the right, we can say that f is getting closer to 3. We could even probably say that the limit is equal to 3, but we want to just take a few precautions before we do that. And so first, even though f is getting closer to 3, that doesn't mean f of 2 is equal to 3. F might not exist at 2. We don't know. And actually, we don't even care, really. We don't care what happens at x equals 2 right now if our limit does exist and we can find it. Later on, we'll care about x equals 2, but right now we don't. And lastly, as x approaches some value from the left and the right, x equals 2 maybe, we might get a different height. And that's not a good thing. That would mean the limit doesn't exist. All right, so let's give a sort of informal definition of limit and just basically explain what's happening. So we say the limit of f as x approaches c is L, and we have our notation for that there. If we can make f as close to L as we wish by making x sufficiently close to c from both the left and the right. So what that means for us is f approaches L as x approaches c. So if we want to know what the limit of a function is, if we want to push f towards its limit L, we just keep pushing x towards c. And if it actually is its limit, it'll work. So there are a few cases where a limit is not going to exist, for sure, every time. And that's if the function's oscillating up and down at x equals c, like in this case. We can't even tell what's happening at x equals 0, which is our c value here. Secondly, if we're riding left to right, we just fall off the graph. There's a jump in the graph, meaning we're approaching x equals c from the left and the right, but we get different heights. And then lastly, if we have a vertical asymptote at c, meaning the graph goes off to infinity at c. All right, so let's look at another limit problem here. We want the limit as x approaches 4 of x minus 4 over the square root of x minus 2. So we know already if we just plugged in x equals 4, it's not going to work. So here's the graph of this thing. And we want to let x equal 4 and see about what height we're at. So again, from the left and from the right, and it looks like we're approaching 5. So let's say the limit as x approaches 4 of f, in this case, is equal to 5. But again, we're building a table here. It's pretty much an approximation. All right, so remember we said that the limit as x approaches c has nothing to do with f of c. So look at this case right here. If we have x squared minus 1 over x minus 1, There's a jump, or basically a hole in the graph at x equals 1. And so the limit as x approaches 1 is 2. That's the height we're at from the left and the right. But the function is undefined at 1. So now for a similar function that is almost exactly the same, we're going to take that same line with the hole in it, but now we're going to put a value for x equals 1. So if x is equal to 1, then y is 3. And so in this case, the limit is still 2, but if we evaluate the function at 1, we end up with 3. So again, we can't just plug in 1. And one more time. In this case, h of x is x plus 1. If we want the limit, we're going to get 2. If we evaluate the function, we get 2. So in this case, it works. But it's just basically an ordinary line. We don't even need that dot there. We'll just continue the line. All right, so limit laws. First, we want the limit as x approaches c of k. And k, remember, is just a horizontal line. So if we pick any c value here at all, how high up are we? We're always at k. And that's why the limit as x approaches c of k is equal to k. Next, we want to find the limit as x approaches c of x, and that's going to be equal to c. So if we look at the line y equals x, that's the function, and we go over to c value, some c value, and go up and over. Since y is equal to x, we're still at c. All right, so we'll define those first two limit laws, and then we'll define the rest. We can add, if we're adding them, we can break them apart. We can pull out a constant. If we multiply them, we can pull those apart. Division, and if we have an nth power, we can bring that outside. And in class, we show that we can basically find any rational function's limit using all of these different properties and ending with number 1 and 2. So let's say we have this limit. The limit as x approaches 3 of negative x squared plus x plus 2 divided by x cubed minus ax minus 2. So first, we can say that we have the limit of the top over the limit of the bottom, and that is by number 6. Next, we can take the limit of each individual term in both the numerator and the denominator, and that is by number 3. Next, we can pull out the constants. So that negative x squared at the front there, that has a negative 1 technically. And down the bottom there, we have an 8, negative 8 that we're pulling out. That's by number 4. All right, so by 1 and 2, all we have is the limit of x and the limit of a constant to work with, and that's all we need. So we end up with negative 4 over 1, or negative 4.